Hello and welcome to day 2. What we're going to do today is we're going to organize all the matter in the universe. So that should be easy, right? Um, One of the things that's really going to help us if we have kind of a visual here for the various parts of matter that we're going to classify. We're going to go through this entire sheet. I should mention that this is available as a resource guide that, somewhere below this where you found this video on the Canvas site. So a couple of things that you'll probably recognize right away is those two concepts that we kind of talked about in one of the very last videos, having to do with physical and chemical. One of the reasons that I kind of introduced that on the first day is that this is really how chemists have classified all of the matter that we see around us and a lot that we don't see. You'll notice that if you have a bit of matter, there's 3 different phases, unless you're a dorky physicist. There's actually a 4th state of matter named plasma, but it's kind of out of the scope of this class, so we're just going to pretend that it doesn't exist and go na 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 na. So we're going to talk about solid, liquids, and gases. We're also going to talk about that kind of first major division between mixtures and also substances. Honestly, that word pure doesn't really need to be there. Just by calling something a substance, turns out you're automatically calling it pure. So let's start at the top with the solid, liquid, and gas. You probably are totally familiar with these concepts, but I'll introduce a bunch of new vocabulary that hopefully will confuse you. So probably the substance that we're most familiar with is water. Here are the 3 different phases of water. Obviously, we just call them gas, liquid, and solid. One of the things that we're going to develop over the course of these next few lectures is something called the particulate theory of matter. It's this kind of revolutionary, or at least it was revolutionary, 200 years ago, this idea that all the matter that we see around us and a whole bunch that we don't is made up of these little tiny spheres that are connected together, or sometimes not connected to anything else. But one of the things you'll notice in this kind of non-moving demonstration here is that when you have a solid, that thing is really kind of a dense assembly, a semi-dense assembly of all kinds of different molecules in this case. Liquid, we've got this kind of tumbling mass of stuff. And then gas, you'll notice that they kind of start to spread out a little bit. Another thing which you'll notice here is these little Mickey Mouses. That actually is the H2O of that thing that we call H2O, right? Those 2 little white spheres are hydrogen atoms, and we'll talk about atomic theory probably very quickly. And that single red sphere is oxygen, and you'll notice that that's what makes H2O H2O, right? So as long as this unit kind of stays together, and if we were to change it in any way, that would actually be a chemical change. That's not what we're talking about here. All of these changes in state as you go from gas to liquid to solid, these are all physical changes. Refer back to that last lecture if you're confused about what makes something a physical change versus a chemical change. But here's a classic example. So one thing you'll notice about this sample, which is actually in the solid phase, is that even in the solid phase, all those little particles that make up a given sample, obviously this isn't water, let's actually switch it to water. You'll notice that they do have a certain amount of motion. And as you might expect, if I were to cool this thing down, that motion kind of gets less and less and less. But the point is that even in the solid phase, even things that you're looking at in the solid phase, actually turns out that if you were to zoom in really, really far on those little tiny particles, they're actually kind of vibrating a little bit. And that's gives rise to all kinds of interesting concepts in chemistry that we'll kind of explore throughout the term. And another thing which we could do, obviously, is we could heat this thing up. And what's going to happen as we heat this thing up, first of all, you should know the name of that phase change is melting, right? So if you take something that's in the solid phase where they're just kind of all shaking around a little bit, and then you go to the liquid phase, it turns out what happens is that you start to give a whole new kind of motion to these little particles. You'll notice that some of them are kind of spinning around. They're actually doing what's called translocating from kind of one spot to another. That's something that doesn't happen in the solid phase. As we continue to heat this thing up, you should know that this is evaporation or boiling in this case. I'm actively trying to get something to boil. You'll notice that that motion becomes more and more intense until, oh, you see it? That little guy right there is moving around now. So that is gas vapor at this point. So you've got a bunch of liquid, a little bit of gas vapor up here. And as we continue to heat it, obviously we get more and more things into the gas phase until they're all in the gas phase. So if you kind of notice some of the changes in motion that we have going on here, we should probably go back to the solid and just talk about one step that is actually really tough to do, and that is to take that motion out completely. If you ever hear somebody talk about absolute zero, that's where you've actually gotten all of these little vibrational motions to stop. It's not something that we've been able to achieve just yet. But if you kind of keep this particle theory of matter in your head, a lot of the kind of physical properties that I'm about to talk about having to do with these different phases are going to be a little bit more apparent. One thing I really should mention to you is that this website right here, this PHET from Colorado University, has some really awesome kind of simulations of different chemical phenomena. And we're going to use this throughout the term, but I included the link to that particular applet right there. Okay, so let's talk about a few of the physical properties of gases, liquids, and solids. First of all, one of the things that you'll notice, and when we looked at that particulate theory of matter, you notice that gases had a whole bunch of space in between them, and they kind of started to conform to the shape of the container. We would call that in chemistry indefinite shape. And also the fact that they completely fill whatever container they're in, if you give them enough time to kind of fuse through the air, that's called indefinite volume. So one really important way of identifying a gas is that it has that indefinite shape and also an indefinite volume. And as we kind of work down our list here, you'll notice that we kind of change a few things. Well, liquid, right? They're moving around, but they're not moving around quite as much. And they do conform to this shape of their container, so they still have indefinite shape. But one thing they do have is a definite volume, right? In other words, if I had some sort of liquid that was existing in some sort of beaker, and I poured it into a different beaker, it would conform to the shape of that container, but it would still have it would still occupy the exact same amount of space. And so that's one thing that's very different about gases. And then, of course, you might imagine, if you've ever seen an ice cube before, is that solids have their own definite shape, and they also have a very definite volume. So that's these are kind of two different concepts that we can kind of work ourselves through the phases with. And also it kind of allows us to start talking a little bit more specifically about these other classes of matter. One thing that was always kind of blew my mind is this idea that you can actually have a solid, liquid, and gas of any sample of matter, right? You can have gaseous iron, right? And it's bonkers to see, but it's certainly possible. You certainly could imagine like at a smelting plant or something like that, you've definitely seen liquid iron. But it turns out that at least theoretically, all different matter can have those three different phases. I should mention that if you go from solid to liquid, that's called melting. A liquid to gas, that's called either boiling or evaporation. The harder words are the ones going back the other way. If you go from a gas to a liquid, that's called condensation. And then from a liquid to a solid, well, that's just freezing, essentially. There is another word for it, but don't worry about it. And it turns out that we're going to see a bunch of different demos as kind of videos in this class. One of the demos is going to involve something called carbon dioxide or dry ice. And what you're going to see there is the ability to actually skip the liquid phase altogether and go from a solid to a gas. That is called sublimation. And the reverse of that, which is a little bit harder to remember, and I might actually include this as kind of a chalk talk kind of thing, but going from a gas to a solid is called deposition. So let's work our way down to this very first division between in matter, right? What we have is a mixture and that has what's called a variable composition, and I'll explain that in just a second. And then you have a substance, or a pure substance, which is said to have constant composition. So when you see a mixture, it is by definition two or more substances. And the important thing that differentiates a mixture from any kind of substance is you can separate them by some sort of physical means, right? And so think back to that when we talked about physical changes. What does it mean to say that you can separate them by physical means? Well, you could boil, say, a liquid away from salt water, and you'd end up with salt and water, right? That's a perfect example. Salt water is an excellent example of a mixture. And you obviously could collect both the sodium chloride and also the water that's in there, and they would both be considered substances, right? And so anything that you can think about where you can use one of those physical means and separate them, it can be just as simple as, let's say, taking a certain type of rock away from another kind of rock, right? That's also an example of a mixture. Rocks are just mixtures of a whole bunch of different random substances. Sometimes not so random, I guess. And then also, I should show you this slide because this kind of gives you the idea that just about everything that we can think of, and a lot that we can't, really is going to be a mixture, right? And this is where chemists get really specific about their definitions. If I was to say that, you know, the wedding ring on my finger is gold, right? You probably would be like, not that impressed, right? Well, it turns out if I start to try to classify that as a substance, though, it gets a little bit more complicated, because it turns out that, yes, the primary component is gold, but gold is actually a substance. And the thing on my finger right now, the wedding band that I'm looking at, is certainly not just gold. It's actually an alloy, right? It's actually a type of mixture that I could separate into all of its component substances. Of course, gold would be a major portion of it. Knowing my wife, there's probably uranium in there. And there's certainly all kinds of different metals that are put in there to kind of make sure that it doesn't, you know, fall off of your finger, because pure gold is actually pretty soft. And if you have any, please send me an example of it, and I'll definitely show that in the demo and not try to sell it. So this slide, the whole idea is that just about everything that you can think of that is matter is really probably going to be a mixture, and then you can kind of work harder on that mixture and separate it into all of its different substances. And then those substances we'll eventually talk about could either be elements or compounds. Most substances are actually compounds, but we'll see that in just a second. Well, let's go back to that flow chart. And so we've already talked about matter and the fact that any piece of matter can at least theoretically be in either a solid, liquid, or a gas physical phase. We talked a little bit about mixtures and pure substances. What we're going to do now is we're going to double down on kind of the mixture side and talk about what does it mean to have variable composition. Well, it turns out that if you imagine an example that you know to be a mixture, like let's say salt water, variable composition means that I can put as much water or salt in there and it's still going to be salt water, right? In other words, I could have a whole bunch of salt, I could have just a little bit of salt, it's still a mixture of salt water. That's kind of classic that's classic to mixtures, is that idea of a variable composition. On the other side here, if you look at this darkened area here and imagine something that you know to be a substance like water, right? That's said to have constant composition. You'll remember H2O, right? That means that I have to have 2 hydrogen atoms and 1 oxygen atom, right? If I change that at all, it is no longer a substance known as water, right? That means that water must therefore be a substance, right? Constant composition, this of course leads to one of the classic jokes in chemistry. The classic joke is 2 people walk into a bar and one of them orders H2O and their friend says, "I'll have H2O too." And then the friend throws up because they drank H2O2, which is hydrogen peroxide. Stop laughing and concentrate. So you can think of all kinds of different mixtures probably, and it turns out that we further subdivide them into what's called heterogeneous mixtures and homogeneous mixtures. So let's get a couple of definitions for these guys. Oh, keep in mind, there's a resource guide there that'll help you kind of keep all these definitions straight on an exam and on your homework and such. So what makes something a heterogeneous mixture? Well, I always think if you can see boogers, that sucker is a heterogeneous mixture, right? And so the fancy way of saying that is that several phases are present, right? Do you see layers, or is there some sort of floaty in there? That's by definition considered a heterogeneous mixture. I'll show you a couple of different examples of a heterogeneous mixture.
So I wanted to take a second just to show you a couple of examples of each different types of these matter. So this is a perfect example of a heterogeneous mixture right here, this Newman's Own olive oil and vinegar salad dressing. So here you can see a whole bunch of different phases, right? Obviously you can see the layer in the bottom and the layer in the top, right? So this is kind of like that typical example of like oil and water. And it turns out even if I try to mix this thing up, we can still kind of see boogers in it, right? It will eventually settle out, but even if it didn't settle out, that would still be considered a heterogeneous mixture. Another kind of more simple example of a heterogeneous mixture is something like this, right? Obviously, you've got a variable composition here. I could have a whole bunch of more yellow rocks, and it would still be kind of like, called the same thing. By example, in order to separate these two substances away from one another, I could take all the blue rocks and physically separate them from the yellow rocks, right? So that's kind of like a really good example of a mixture.
And then we have something called a homogeneous mixture. This is said to be uniform throughout. We actually, because we're chemists, we come up with 7,000 different ways to say the exact same thing. So if you ever hear the word solution, it turns out you're talking about something that's a homogeneous mixture. And this idea of homogeneous is just that if we were to kind of take a spoonful of this particular mixture, we would always end up with kind of the same components. And that's different than a heterogeneous mixture, because if you kind of took out of one layer, you're going to have some very different composition than if you took out of a different layer. Another couple of vocabulary words having to do with homogeneous mixture is this idea that you have a solute, the substance that is dissolved, and a solvent, or a substance that does the dissolving. And our classic example of a homogeneous mixture, which is salt water, obviously salt would be the solute, and then the solvent would be water.
So here's an example of a homogeneous mixture, also called a solution. One thing that you'll see quite often in a chemistry lab, you'll see this big M that stands for something that we'll talk about later in the term, which is it's called molarity, which is a measure of concentration. But obviously I've got two substances. Well, I guess it's not obvious. I got one substance, this copper 2 nitrate in here. The water, it's dissolved in water, so that would be said to be the solvent, and then the solute would be this copper 2 nitrate. Other types of solutions, homogeneous solutions or homogeneous mixtures are like this guy right here, right? So that's a hydrochloric acid solution right there. Other are a little bit more easy to think about. So like air, for instance, if it's a purified air without dust and particulates floating around, that's also a good example of a homogeneous mixture.
So if you click on this link, it should bring you to the animation I'm going to show you in just a second here. So we have talked a little bit about the particulate theory of matter, but I thought it would probably be a good idea to kind of show you what's happening in kind of a typical saltwater mixture. So this guy is going to shake out a little bit of salt, and you'll notice what happens is that all those little particles start to kind of spread apart. Those are going to be called cations and anions in a little bit. But one of the things that's missing from this is that really water should have its little Mickey Mouse ears all floating around, but that thing is present in such a high amount relative to the sodium chloride that we're not picturing it here. So keep in mind, we're going to be going back to this particulate theory of matter. Well, you might say, well, what about something that is, let's say, a heterogeneous mixture, right? So this is the way that we could show a homogeneous mixture, and it's got variable composition, so I can keep adding more, and it's still salt water. And I could just make it more and more concentrated. Well, what about something that we would consider a heterogeneous mixture? What would that look like? Well, for this one, it turns out to be strontium phosphate. And you'll notice that we're going to hopefully get to a point where it becomes a heterogeneous mixture, and it just kind of all collects on the bottom. And you'll notice that this would be a great example of something that macroscopically would have, what I said was a booger in it. So there's your big giant booger, right? There's a different phase from the otherwise liquid phase that we see up here that has some other particles dissolved in it. So another thing that I wanted to mention is that a solution can really be any phase of matter dissolved in any other phase of matter. Typically, what we're going to be talking about when we talk about a solution is like a solid or a liquid or a gas that's dissolved in a liquid. So examples of each of those, well, obviously a solid dissolved in a liquid could be like sodium chloride, right? Salt water. Liquid dissolved in a liquid would be something like, I don't know, whiskey, right? Where there's a whole bunch of ethanol that's dissolved in water with a bunch of other stuff. Gas being dissolved in a liquid, that's actually what fish are going to breathe, right? They actually breathe the little O2 gas molecules that are dissolved up in the water. And you can think about some other probably slightly more common things, like I talked about my wedding band, which is a mixture of a bunch of different metals, right? So a whole bunch of different solids all kind of mixed together. That's an example of an alloy. But there's all kinds of crazy examples of, let's say, a gas dissolved in a solid, or a solid dissolved in a gas, like aerosols and things like that. It's just kind of a really kind of odd thing to think about. And unfortunately, if we were actually in class, I could show you an example of a whole bunch of the really cool ones.
All right, so here is that wedding band I was referring to, right? So that is actually considered a homogeneous mixture as well. This is a special kind of mixture called an alloy, which is one solid dissolved in another, actually several solids dissolved in another.
So now what we're going to do is we're going to kind of shift over from talking about mixtures that, of course, have a variable composition, and we're going to start to talk about substances. Those have constant compositions. Well, it's probably good to take the simplest kind of substance, which is actually an element. And the definition of element is that it cannot be broken down into simpler substances by any ordinary chemical means. Keep in mind that the way that you take a compound and turn it into its constituent elements is through some sort of chemical change, right? So we had physical as kind of being the dividing line between mixtures and substances. Now we have that chemical change dividing line between compounds and elements. But really the most simple building block of anything is an element. And you'll probably recognize this term atoms. It turns out that's the smallest portion of an element that retains the properties of the original substance. Right? So we've got elements, can't be broken down any further into something that is a simpler substance. And each one of those elements is made up of a whole bunch of different atoms of a particular type. Well, what happens if you take two different kinds of atoms or two different kinds of elements and combine them together? Well, that's where you get a compound. Turns out compounds are really two different types. One is called a covalent compound, another is called an ionic compound. I will talk a little bit now about these, but we're going to learn a whole bunch more about these. So covalent compounds, what makes something a covalent compound? Well, turns out if you talk about something as a molecule, you are talking about a covalent compound. Molecules are something like water, right? Where you've got two hydrogens and one oxygen. They're two different types of elements that are tightly bonded, and those two things act as a single unit, right? If you take one H away from your H2O, that is no longer water, right? That's classic for something which is a covalent compound. Ionic compounds are a little bit different. These things are actually like sodium chloride would be an example of an ionic compound. You need to have a non-metal and a metal, and we're going to talk, like I said, about this a whole bunch at the beginning of next week. But for now, let's just get the definition down. Ionic compounds are made up of positively charged cations and negatively charged anions. I should mention that the way that I always used to remember this, because I had actually a pretty bad memory, is that T in cation reminded me of a plus sign. So that's the plus side of things. And anion, that N stands for negative. That's just a little trick that you can use to remember the difference between a cation and an anion. If we were in the actual lecture classroom, you would see this gigantic periodic table of the elements. Unfortunately, you're not going to be able to stand up and salute it like I always have everyone do. But this is a list of all the different elements that we have discovered and made. And we're going to talk a whole bunch about the kind of way that this table is organized. But this is available as a resource guide on Canvas. But what you'll notice is a whole bunch of different elements. Like for instance, if you're ever asked by a jerk someday on an exam, is blank an element or a compound? Well, it turns out if you can't find it on this sheet, it is a compound, because these are the only elements that we know of in the entire universe. We're going to talk about element symbols. One of the things you'll notice is that there always is a capital letter followed by either nothing or a lowercase letter. And each one of these things corresponds to a particular element. So more on this as the class progresses. Another thing that we should mention about this periodic table of the elements is that in general, if you find something, let's say we talked about iron before, and you talk about elemental iron, well, it turns out that iron can just kind of exist as a single atom, right? And so those are called monatomic elements. Cobalt is another example of a monatomic element. The first thing that I really would like you guys to memorize, though, is that there are a few elements that actually need a buddy. So in other words, they can't just exist at normal temperatures and pressures as just a single monatomic element. What they have to do instead is become what's called a diatomic element. And it turns out that the 7 that do this actually make a 7 on the periodic table. So here we'll notice that this kind of area of the table here kind of looks like a 7. So if you're ever asked by some jerk someday, what are the diatomic elements? You say, oh, I remember there are 7 of them. And they even make a 7 on the periodic table. They are nitrogen. That has to be an N2, right? In other words, they have to be 2 nitrogens bonded together. They can't just exist like iron as just a single atom. It has to be O2, F2, Cl2, Br2, and I2. And one of the weird things is, even though it makes a 7 on the periodic table, you'll count those up and notice there's only 6 of them. Where the heck is the next one? Well, it turns out the one exception that is almost the exception to every single darn rule that we're going to talk about is hydrogen. So that's kind of your beginning of understanding how this periodic table is organized. The 7 diatomic elements. Keep in mind, any exam, you're allowed to use this periodic table of the elements. It's just a really helpful thing to remember what the diatomic elements are. And of course, hydrogen's always its own little camper over here. So let's put those 7 diatomic elements into our little guide right here. It turns out these things are called diatomic molecules, and there they are. Here's a different picture of the way that those 7s are organized here.
All of these are considered substances now. Notice that I didn't call any of the things that you saw in, when we were talking about mixtures. I never called them substances, right? And so like this guy, which we saw before, this was a homogeneous mixture, right? I can't call this a substance, but it turns out that I can very easily call this a substance, right? This is actually distilled water, right? In particular, this would be considered a compound, specifically a covalent compound if you get to the end of this lecture. This guy, this copper sheet right here, this is pure copper, right? So I can call this a substance. This is an example of an elemental substance, right? And so just to kind of show you that wedding band right here, I can't call the metal in this a substance. This is actually an alloy, so that's a mixture. So you can kind of see it's sometimes tough to tell and classify. Sometimes you need a little bit more information to classify something appropriately. Here is something with constant composition, just like every substance should have. And you'll notice that this is an example of an ionic compound. Again, just wait until the end of this video lecture, and that should make a little bit more sense. Here is another substance. This is known as mercury, right? And so this is pure Hg right here. Super duper heavy. We saw that before.
So going along with that particle view of matter, keep in mind that we can also organize things according to our chart that we were just looking at in terms of classifying matter. But instead of looking at it kind of macroscopically, we can actually look at the individual particles here and also put different representations into the chart. What I mean by that is that we can talk about a sample of matter showing just this particle diagram, and we can assign it certain things. Well, we can assign it certainly as an element, right? Because we only have spheres of a certain color. So for instance, this might be probably a gaseous iron, for instance. You could say that that is a particle diagram for gaseous iron because we know iron can exist as a monatomic element. And the fact that we know that this thing is an element is that we only have a single type of sphere, I guess you could call it. Well, how the heck are you going to show, say, the diatomic elements? Well, this is a way that you could show the diatomic elements, right? We've got the two atoms bonded together. This could be, say, oxygen gas, right? We're going to work with this probably a little bit more on day 3, but I just kind of wanted to introduce it at this point. Another couple of words that you're going to hear me use quite often are things like monoatomic or monatomic. They are all monatomic because they're consistent. Each one of those particles consists of just a single atom. These are diatomic, right? Because we have two different spheres connected together. Is an element because they're both blue. Well, what would happen if one of these little blue spheres, right, if we took every single one of these little diatomic doubles right here, and we made, let's say, one of those blue spheres, let's say, orange. Well, that would be something, if every single one of these was a blue and an orange sphere, that would be molecules of a compound, right? A compound is something that has to be made up of more than one type of element. So here is an example of another type of compound, right? You see these guys actually have 4 little spheres connected together. So that's a monatomic element, a diatomic element. If all of these things were 2 different spheres that are different colors of the same type, those would be considered molecules of a compound. Here we have molecules of a compound, and you might say, well, we've got monatomic and diatomic. What the heck do you call it when there's 4? Well, this is an example of a tetraatomic compound. And then, so what do mixtures look like? Well, here's a representation of a mixture, right? You'll notice that we've got all kinds of different things all mixed together. And specifically, you could, looking at the particle diagram, talk about it as a mixture of 2 different elements. Right, there are the 2 different element types there, and a compound. There's the compound, right? And keep in mind, I could also change this from the gas phase to the solid phase and things like that. So that's what we'll talk about a lot more in day 3.